You are listening to the PFAS Research and Remediation podcast series, produced and created by Arcadis, with funding from the Environmental Security Technology Certification Program, ESTCP, grant number ER23-7692, through the United States Department of Defense. All opinions, interpretations, and conclusions expressed belong to the hosts and guests and do not represent views or policies of the Department of Defense, Arcadis, or guest affiliations. In this first season, we're focused on PFAS and interview a broad panel of experts who have each contributed to the growing knowledge base around remediating this emerging chemical of concern.
Today, we'll be speaking with Dr. Marc Deshusses. Marc is a professor of civil and environmental engineering at Duke University in beautiful Durham, North Carolina. Our conversation today focuses on supercritical water oxidation, or SCWO, for complete PFAS destruction. PFAS are difficult to destroy thanks to their carbon-fluorine bonds, which is one of the strongest bonds in organic chemistry. Most conventional drinking water and wastewater treatment processes have been ineffective in removal or destruction of PFAS. However, SCWO has shown promise for near-complete destruction of PFAS in field and laboratory testing. SCWO has been used since the 1980s to successfully treat a variety of hazardous waste, such as polychlorinated biphenyls or PCBs. In this project, we discuss how this technology can be used to destroy high levels of PFAS in water. I'm Dr. Theresa Guillette, a technical expert with Arcadis, and I'll be your host today. Marc, thank you for providing your time to do this podcast and highlight some of your work on PFAS. Before we get started, can you give me a brief summary of your position at Duke, 374 Water, and your technical background and areas of expertise?
Thank you, and thank you very much for having me. It's a great pleasure and an honor to talk about my passion here. My name is Marc Deshusses. I'm actually a chemical engineer working in environmental remediation, waste to energy. I'm a professor at Duke University, and I'm also the co-founder of 374 Water and head of technology.
You have done a lot of work with ESTCP over the past decade, working on both perchlorate and PFAS. How did you get started working on PFAS?
Yeah, that's true. I actually have been all in my entire career working towards environmental remediation, waste to energy projects, started working on MTBE, and then perchlorate, chlorinated solvents, and then most recently on PFAS. And we need to go back to around 2013 when the Gates Foundation at the time looked at the situation, the sanitation crisis, the situation around the world. And maybe not all the listeners know that in this world, there's about 1 billion people who don't have access to a toilet and have to practice what is called as open defecation. And there's 4.5 billion people whose waste ends up in the environment untreated or partially treated. And so back in 2013, the Gates Foundation launched what is known as the Reinvent the Toilet, funding a number of projects to figure out new ways, new toilets, and new ways to conduct sanitation of fecal waste or toilet waste. And so at the time, I pitched the idea of using this technology that we'll be talking about called supercritical water oxidation as a way to treat fecal waste at a neighborhood scale. The idea is to have a treatment in a box and being able to take toilet waste and turn it into clean water, recover nutrients and fertilizer, and doing it in a sustainable and energy efficient waste. And as we progressed with our project, I got to talk with my colleagues here at Duke University about what their passion was, and they were working in PFAS and finding emergences of PFAS in a number of wastes. And I said, well, it'd be interesting to see whether our treatment in a box can also treat PFAS. And at the time, not much was known about how PFAS could be treated. And so we set up a simple run where we spiked 1 ppm of PFOA and PFAS into our treatment unit. They said, well, it's kind of crazy. This is a very high concentration. 1 ppm is a million ppt, so a fairly high concentration. And to our surprise, there was a non-detect in the effluent. So this is how we got started. And we realized that supercritical water oxidation could treat PFAS, and led to us writing a proposal to ESTCP and funding of a demonstration project for complete PFAS destruction.
That is correct. You are PI for ESTCP project ER205350, supercritical water oxidation for complete PFAS destruction. There's a lot of interest in this project, both from DoD side as well as in commercial sphere, mainly because it's a technology that offers one of the only potential solutions for complete PFAS destruction. Can you briefly describe what SCWO is and how it can lead to PFAS destruction?
So, SCWO is the short for supercritical water oxidation. So what is supercritical water? So we used to think of water coming either as a liquid, a gas, or a solid, but there's actually a fourth state of water. If we take water and we heat it above 374 degrees C, and that's 705 degrees Fahrenheit, and we compress it to roughly 220 times atmospheric pressure, water becomes supercritical. And it's the fourth state of water. It's neither a gas nor a liquid, but it has amazing transport and reactive properties. For instance, oxygen is fully soluble in supercritical water. And what that means is that if we are taking any organic waste in its aqueous form, and we heat it to above the critical point and compress it and inject air, all organics are going to rapidly get oxidized and be mineralized to their most stable form. And that includes PFAS, emerging contaminants, microplastic, PCBs, and so on. So it is an amazing way to destroy some of the nastiest and most persistent contaminants.
That's really amazing. I had no idea that in addition to PFAS, you can also use this type of technology for really complex waste streams, say microplastics or other. Is there a particular contaminant class that this doesn't work for, say heavy metals or anything like that?
So it really is a great solution for all organics. So it's going to mineralize all the organics. Now, of course, a metal going into the supercritical water oxidation system will come out at the tail end. So it may transform it, concentrated it, some of the minerals, but it's really a great solution for organics. And, you know, when I think about some of the attributes and some of the advantages of SCWO, I see this ability to handle just every organic as being one of the main advantages. So it doesn't matter whether, you know, going back to PFAS, it doesn't matter if the PFAS is mixed with some surfactants or cleaning solution, detergents, or other contaminants, maybe hydrocarbons or chlorinated solvents. They will all get oxidized and mineralized in the process. So that's one of the great advantage of the technology compared to other technologies. And with respect to PFAS, what we've demonstrated is that SCWO has the ability to mineralize and convert all the PFAS to their most elemental form. I think in terms of the drawbacks, what I'll mention is really three limitations as I see them. One is because of corrosion, we need to be careful with solutions that have excessive salt concentrations. So, you know, very high chlorine or even the most concentrated PFAS, AFFF solutions, they need to be diluted before we can handle them. Currently working towards systems that can take neat AFFF. Second limitation is in order to treat the waste, we need to be able to pump it. And what that means is that solutions that have excessive grit, you know, sand, heavy soils, is a limitation as well.
So in that regard, you really can only do like liquid and slurry stream, nothing solid, nothing very like particulate matter.
There's a particle size cutoff, and it's really physical limitations of the pumps and the check valves. So if currently we think of particles cutoff size at around 3 to 5 millimeters. If it's larger than that, the check valves won't completely close. And then we have difficulties in pumping. But we think that the process can lend itself well for soil treatment, but we would need a different system that we need to develop.
So maybe combining something like soil washing with your thing?
Soil washing, we've been looking at the different soils fraction. Definitely there's something called soil fines that are smaller than 60 microns, and these look more like a paste. I think we can definitely handle those. And then you mentioned earlier a miniature SCWO, a mobile system, being able to treat on site. I think this is really one of the great attributes of the technology, and also the vision of 374 Water is to have systems in containers so they can be transported and provide treatment where it's needed. Because of the energy required to heat the waste and bring it to the critical point, this technology lends itself best for the more concentrated forms of waste. And so for like large streams of contaminated groundwater or drinking water, probably the best way of addressing this is by first concentrating the PFAS onto activated carbon, ion exchange resin, or maybe with foam fractionation or other concentration technology, and then treating the concentrate in the SCWO systems. SCWO is a great technology to treat a large amount of PFAS. That is really, I think, one of the great attributes of the technology is the ability to treat a large mass in a small volume system.
I see in your recent ESTCP webinar, you mentioned there are no byproducts with this process compared to, say, something like incineration. So that would be a major bonus for this treatment of PFAS and liquid waste, correct?
Correct. Yeah, this is a great plus for the technology. What we have is we have demonstrated that any PFAS, whether large, high molecular weight or low molecular weight, or ionic or non-ionic, or all precursors, organofluorine, all of them get fully mineralized to CO2, water, and with breakage of the carbon to fluorine bond and release of inorganic fluoride. Unlike other technologies, SCWO is, we call it PFAS agnostic. It will treat every PFAS, as I said, and we don't form volatile species. There's some report about incineration breaking large molecular weight PFAS into smaller volatile PFAS. And we've demonstrated that the lower molecular weight, like TFA or PFPRA, are equally mineralized during supercritical water oxidation.
In your project, your group defined success as the ability to consistently treat waste below the regional screening levels. As we move towards lower and lower regional screening levels and even lower health advisory levels from EPA, do you think that this technology can keep up with these new demands?
Yeah, this is a great question. So, we wrote what you quoted at the time of writing of the proposal, which was a couple of years ago, knowing that probably the target levels were going to be moving targets as we know it, and we know how low the health advisory limits are. Now, as I mentioned, SCWO is a great technology to treat a large amount of PFAS. We know we can tune the destruction efficiency, meaning we can decide how many log reductions we will achieve with those systems by tuning the temperature and the reaction time in the system. We know we can get down to single-digit PPT levels. It depends to some extent on which PFAS. But what we think is that if we need to get to really, really low levels, we might actually tag on some other technologies to do polishing of our effluent. Maybe granular activated carbon or ion exchange at the tail end of a process, also for safety. But the beauty of it is that we know that we can treat these GAC and IX resins once they're fully loaded in our system, providing a complete treatment system.
I really love that you first started off working kind of in developing countries for this technology and thinking of how to transition that from PFAS to, say, an international space. Is 374 Water getting into that, or are we primarily thinking about U.S. places?
Being faithful to the original intent is very important to us and to me personally. I still think that I'd like to see our units deployed in developing countries. It'd be very rewarding to see a unit treating fecal sludge in this context. So it's a goal of mine to see it happen.
So kind of thinking analytically, do you have certain numbers that you want to get below, or are you looking for something else to pop up when you say destruction, like say just a fluorine molecule?
I mean, it is both. I mean, definitely we want to provide effluent that is clean, that has no PFAS below detection limit or low concentrations, depending on the context and what we treat. But we also want to show that the organofluorine atoms are recovered as fluoride. And that's one of the things that we can do very well because the system is fully enclosed. We know exactly what enters our systems, and we can capture everything that leaves the system and show these fluorine balance. And as such, going into the future, those systems will be able, when they're running, will be able to provide certificate of destructions, the proof that the PFAS has been eliminated and mineralized.
As we wrap up, are there any further points that you'd like to make about this project, technology, or the challenge of PFAS in general?
I'm super excited about where we're at right now. For me, this is really why I get up in the morning and I'm motivated doing what I do, is being able to develop solutions and see them being deployed. So I'm really excited about the year to come and the demonstrations that we have and the commercial deployments as well.
Well, thank you again for your time today. I know that I'm really excited about this project going forward and the idea of potentially destroying these PFAS. So thank you.
Thank you.
Thank you so much for listening. This podcast was funded by ESTCP and produced by Arcadis. The interview was conducted by myself, Dr. Theresa Guillette, and our guest today was Dr. Marc Deshusses. If you're interested in more information on ESTCP's work on PFAS, please visit serdp-estcp.org. Click on Focus Area at the top and select options for PFAS and AFFF from the menu that appears. If you have conducted your own research on PFAS and are interested in sharing your work, please email me at teresa.guillette@arcadis.com. That's teresa.guillette@arcadis.com. And please keep an eye out for more episodes coming soon.